How's it going, everybody? And welcome back to our Cisco Enterprise series. In this video, we're going to be taking a look at the different BGP peering types that are out there. There are two that we're going to be talking about, but we're going to go through and break down how they work. And we're going to be going through some examples of how that comes into play. Now, this is going to be a kind of a longer video. I'm going to be going through a lot of theory and how this works and going through the details of how they come into play and stuff like that. And then I'm going to have a couple of separate videos that are going to be shorter, that are going to be specific to implementation, that are going to walk you through how to do IBGP, how to do EBGP, and then we're going to look at scaling techniques right away so that we can take a look at the full mesh option of IBGP, the route reflected version of IBGP, things like that, and how they come into play, so that we have a lot of native understanding first. Then we go through the deployment process and go from there. So I'm going to go ahead and get out of the way, and we're going to start walking ourselves through this. So the first type of BGP is going to be an external BGP peer, or EBGP. That should be a little e, by the way. So I will go ahead and save that. Neighbors outside my autonomous system. And remember, we talked about autonomous system in the previous video, which is the routers you have administrative control over. Then you have IBGP peer, where our neighbors that are inside of my autonomous system. Update and path selection rules change depending on what type of peer a route is being sent to or received from. And we'll talk about that more in detail later. But there's going to be a lot of information around that we're going to have to understand when it comes to next hop processing and things like that. IBGP versus EBGP peering rules. For IBGP, we have the IBGP packet has a default TTL of 255. So, which means that the neighbors do not have to be directly connected as long as they have IGP reachability between the IBGP peers. IBGP peers typically peer via loopbacks. It allows rerouting around failed paths via IGP, and this is going to be required for MPLS, VPN options, stuff like that. Now, one common question that I get whenever I'm talking to a customer about scaling BGP is, do I have to do via the loopback? And the answer to that is no, you don't have to, but it makes the most sense. And I'm going to actually show you the topology real quick. So let's say, for example, that I want to peer between R26 and R27, or I want to peer between R26 and R60, because remember, we can peer to non-directly connected neighbors as long as we have IGP reachability, which we do. We have EIGRP and OSPF both stood up. Basic implementations at this point in the series, but they're both stood up. So for R26 and R60, I can do a point-to-point peering, gig 01 to gig 0001, right? And I can go gig 000 to gig 1 and do the directly connected peerings across the board. That would work. However, and those are great for directly connected, but for non-directly connected, like 26 and 60 or 27 and 42, what do I do then? Could I peer directly to here? I wouldn't want to. You wouldn't. And remember, I talked about how with IGP, specifically with OSPF, you have the concept of a link and node in the graph. The graph being this square we built out. The links are the transit connections between the routers, the node themselves that owns the interfaces. Well, BGP does the exact same thing, where unless you're dealing with EBGP specifically for a peering to a service provider, you're going to want, for IBGP peerings, you're going to want to peer to the loopback. Because if R26 has one interface go down, say gig 0/1, and R60 is peering to it, this path from 60 through 42 to 61 to 26, that path might go down, but the loopback address would still be reachable via 27 to 26. So it gives you a reason why you would still want to peer via the loopback. So if something did happen, you would at least be able to reach your loopback for non-directly connected peers. IBGP peering configuration is very, very simple. And so the configuration for both is the exact same syntax. Neighbor, the /32 host route IP, remote AS, and then the remote, and then your autonomous system. So your autonomous system number would show up here in the XXX, would be the actual peering AS. So your local AS, where eBGP has the exact same syntax, except for the remote AS would be a different AS. So outside of my AS. Now for peering directly connected neighbors on directly connected subnet, if you are going to if you're going to form a multi-hop peering, so you're going to be peering to another router that is not directly connected to you, you're going to want to use the update source option. So update -source and then say loopback 0, for example. For IBGP neighbors that have multiple paths to each other for redundancy, and it's going to be a multi-path type of situation. You can go two different directions. You can debug IBGP for seeing control plane outputs and debug IP packet detail for information like that. Now, just like with the directly connected peering, you can peer on directly connected subnet, or you can do the eBGP multi-hop. If your eBGP peerings are not directly connected, you still can form an eBGP peering that is not directly connected to you. You just have to have a route to the remote IP address that you're trying to get to. So we're actually going to demo this quite a bit as we get further into. There's going to be scenarios where we're going to have two links between one router and another router for a BGP peering. And then you can load balance over both interfaces. We'll be taking a look at something like that as well. When you get to VXLAN eVPN and you're looking at doing eVPN multi-site, so that's something we're going to be demoing out later on when we get further along in the series, and I will minimize this again, and let me log in real quick. So what we'll end up doing is N73 and N77 are Nexus 9K switches. Well, what's going to end up happening is each of these guys is going to have a loopback address. And so we're going to form an eBGP peering over this connection right here. So 77 and 73 will have a layer 2 VPN connection through the service provider here that we're going to stand up. So 73 and 77 will look like they're directly connected to each other when we do a show CDP neighbors. What will end up happening is we'll do an eBGP peering over the top of that on the directly connected neighbors. So they're going to appear as directly connected. They're not actually going to be directly connected. There's not going to be a fiber running from one device to the other. There's going to be multiple intermediary devices in between, but from a layer 2 perspective, they're going to appear as directly connected. And that's the key factor here. They'll appear as directly connected even though they really won't be. What's cool about that then is we'll be able to do an eBGP multi-hop peering to each other because we're going to be having to pass through another autonomous system number. And what we'll end up doing is we'll do loopback to loopback with the update source being the opposite loopback address. And when we do that, we'll be able to form a eVPN multi-site deployment in order to stretch layer 2 between the data centers. So it's going to come into play down the road, but it's just one of those things where we'll have to stand it up when we get there. So now, if the neighbor's address is the loopback of the neighbor, you use the update source loopback and then the loopback number. Make sure you have a route, be a static or dynamic to the neighbor's loopback. You do have the option of doing a neighbor, the IP address, and disabled connected check is used to disable the connection verification process for eBGP peering sessions. So if you want to turn it off, you can. So just to note that if the eBGP multi-hop TTL is 1, disable connected check is needed. If loopbacks are then the update source, it is also needed. So by default, your TTL for eBGP peers is 1. For IBGP, it is 255. For eBGP, it is TTL of 1. So keep that in the back of your mind. Now this can be modified when you are working with eBGP multi-hop. So BGP adjacency should always be authenticated. So we're going to talk about BGP authentication as well. So it's similar to IGP. So you set a password, but instead of it being it's part of the BGP header, but it's a TCP MD5. So it's a part of the TCP three-way handshake. Security risks with guessing sequence numbers is to reset the TCP connection. So it's a good idea to do the TTL security. So you're going to want to be careful with that. So you can't use both these at the same time. So when we do this, you'll have to choose to turn on TTL security or eBGP multi-hop. Typically, I'll turn eBGP multi-hop on, but then I'll set a password. Non-multi-hop peers must be directly connected by default. It can be modified with peer via loopbacks. Neighbor disabled connected check. If the eBGP multi-hop is a TTL of 1, disabled connected check is needed to form the peering. Update source interface type and number is also needed for the TCP connection. So let's talk a little bit about, hopefully that all makes sense. And we're going to see what this looks like. It's actually really, really simple. And we're going to see this in the demos when we do that in the next video for both IBGP and eBGP. We're going to be doing both, 2 separate videos, one specifically for IBGP and then a second one for eBGP, and we'll go through the process of doing all that. But it's important to understand that at the baseline, your CCNA level of BGP is that you can do multi-hop eBGP peering. You just have to make sure that you have a route to the remote loopback that you're trying to peer to, and 2, that you set the TTL correctly. So a lot of people will just do if you just type in eBGP multi-hop and hit the enter key, what will end up happening is they'll set the TTL to 255 out of the gate, so you don't have to worry about it. But if you don't want to just make it wide open, you can set it down to like 2 or 3 or whatever value you want to. So keep that in mind as well. IBGP loop prevention. Loop prevention via route filtering. IBGP learned routes cannot be advertised to another IBGP neighbor. So because of that, that means that there are some requirements that you need to put into place in order for that to happen. So the way to fix that is this. You either could do a full mesh of peerings, you can use route reflectors, or you can use confederations. Pros and cons for all 3 designs, and we'll dive into this when it comes to BGP scale. But essentially what I want to kind of go into a little bit of detail on this is this. When we talk about this, I did not open up my software to do whiteboarding, so let me do that real quick. I'm going to talk about the 3 different types. I'm going to talk about there it is right there. Sorry for the delay, folks. Let's go over here to medium, and let's do sky blue. So there's the 2 different types of peerings. Actually, let me do red so that it's very, very obvious. So when I do this, when you say full mesh, that means you're peering from, let's assume, loopback to loopback, right? That's what we're going to go do. You're going to be doing this. You're going to be peering from every device to every other device, like this. So logically, all the red lines would be all of your IBGP peerings. So that's what a full mesh would look like. So every router would have a IBGP peering to every other router. The idea is n times n minus 1 divided by 2. That is the equation you need to think of. If somebody says, oh, how many peerings is that going to be? This is what you need to do. So you take n, so in this case here we have 4 times 3. So that's going to be 4 times 4, n minus 1 is 3, divide that by 2, so that's going to equal what? 12. divide that by 2. So that's going to equal out to be, in this case, 2, this is going to equal 6. So I'm going to have 1, 2, 3. So 1, 2, 3, 4, 5, 6 peerings. So that's the full mesh. So that's the thing that you want to keep in the back of your mind when you're talking about peering scale. The other option is what they call route reflection. And route reflection is, in a sense, it's what they refer to as topology hiding. We'll talk more about that later. But just so you understand from a quick picture of what this does, is you would pick like the OSPF designated router, you would pick a device in your environment that would be responsible for learning all the routes from all the other routers in your environment and then passing that information on. So let's say R28 is our route reflector. So remember, we got loopbacks on all these devices that we're peering to. So what would end up happening is R28 would form a peering to each one of these routers. So you cut your peering size in half. What ends up happening now is if I have a BGP peering here and R22 decides to advertise this subnet to me. Well, he advertises that subnet to me, I learn that route out, and then I take 29, being a route reflector client, will then send that update to 28, then 28 will then reflect that out to 43 and to 61 respectively. Now let's assume that 27 is also peered to 43 via eBGP. Well, 43 would get that, and then he would advertise that to 27. 27, because he is fully meshed to all the other routers, 26, 42, and 60, they would also get the update from 27, and then they would be they'd be happy. Now, in these updates, the ASN number is propagated. So let's say, for example, over here we've got AS 101. This is 2, this is 1. Well, what's going to happen is this subnet right here is going to be originated from AS 101, and then it's going to get learned here, right? And the originator is going to be 101. Then this information is going to get passed to 28, 28 to 43, 43 is going to pass it to 27. So you're going to have an AS path of 101 as the originating AS, and then 2, because the traffic has to pass through AS2 in order to get to 1. And that information is going to get propagated all the way around. So your AS path is going to look like this. It's going to be a 2 AS path length with the originating AS of 101. So now the question is, if 60 and 28 form a BGP peering that's via eBGP, let's actually redraw that. This one here, we have an eBGP peering between 60 and 28. What happens then? Well, the answer to that question is simple. We are going to learn that route and we're going to pass it to 28. But what's going to be interesting about it is it's going to receive the route, right? And because the AS path 2 is already in the AS path length, it's going to say, okay, cool, thanks, I've got it. Now, because it already knows about that route. So what it's going to do is it's going to silently drop it. It'll receive the route, right? But it will automatically, it'll keep it in the BGP table, but it won't install it in the routing table. And what will end up happening is if you see at any point you see your own AS path in the AS path list, you're going to drop the update. So this is what they refer to as loop prevention for eBGP. So that's how basically how it comes into play is it looks at the AS path length, looks at the AS path ASs and the AS path length, and then is able to make a determination based off of that. Let's go back over here to our documentation. So when you go and you do this, you can get around the loop prevention by doing a full mesh of iBGP peerings, route reflection, like which we just covered. We're going to cover confederations in a different set of videos that'll come later on down the road. And then eBGP uses the AS path length to do that, and the local AS is prepended to outbound updates. So inbound updates containing the local ASN are discarded. So again, if I receive an update if I'm AS2 and I receive an update from AS1 about a route that already passed through AS2 got learned by AS1, and then AS1 advertises that path back to me, and I see my own AS in the path, I'm going to drop the update. So that is how that comes into play. And the local ASN could be anywhere in that particular AS path length. It could be in the middle. If you're local ASN, if you get an inbound update and you see your AS path in the AS path list, you're just going to drop the update because you already know about the route. And you can modify that neighbor with allow ASN or AS override. Now, depending on the particulars of that, the allow ASN is a customer side configuration where if you, I had this happen once a long time ago, and the short story is I had a junior engineer that I was working with. I wasn't really attached to the project per se, but I had been asked to be there in case he ran into a problem. And so he was like, I want to run with this. This is my project. He wanted to, like, I guess you could say, prove himself. So what ended up happening here was he had taken on this responsibility of standing up. I forget how many locations it was. It wasn't very many. I think it was like 6 or 7. And he was working with a couple of different remote hands at 2 different locations where he was standing up. These were like the important sites. They were trying to stand up on this MPLS VPN environment. Well, long story short is this gentleman did not know about the whole concept of different eBGP peerings. So a different location has a different AS number. And so he used the same autonomous system number everywhere. So he equated that to like EIGRP, ASNs, and OSPF process ID. So that's how he equated it. He didn't know any better. So long story short, when he went to go implement this, I get a call 10 o'clock at night or something like that. He's kind of panicking because he doesn't see any routes being learned. And so I'm like, oh, okay, I said, well, what's your BGP AS scheme look like? And he goes, well, I've got 65,000 or whatever number it was at every one of the remote locations. And I go, oh, that's your problem. Okay. So we simply used allow ASN to allow that. We overrode the AS path loop prevention mechanism and just received the routes in anyway. So eventually the routes were propagated the way that they needed to be, and everybody was happy. But I told him in the future for the remote, the other sites, just give them a different AS path ID and a different BGP ASN, and you won't run into that problem anymore. And so he did. He updated the provider going forward. They were happy to make the adjustment. And when they did, he didn't have any more problems like that. It was a small little snafu. Stuff like that happens in the real world. But, stuff like that happens. So that was the case. Now, AS override is doing the provider side. Where the provider, when you do this, the provider will receive the AS and it will replace the AS you advertise with its own AS. And then pass it along. So it'll look essentially like the provider's AS twice. Because that's essentially what it will be. Even though the originating AS is going to be another value, whatever the originating AS was, they replaced the originating AS with the provider's AS. And that's essentially how you get that done. So, next top significance. Why do we care? Well, the reason we care is BGP is not a routing protocol, right? It's an application used to exchange routing information, specifically network layer reachability information. Prefixes, right? At the end of the day, it's just a prefix. The route details, but not the path details. So because of that, there's a lot of information that can be modified to control how the routes are going through the environment. You have the prefix length, the attributes, local preference, AS path, etc. Next top control. So BGP next top controls IGP route recursion. So BGP knows the next hop but not the outgoing interface. IGP must be able to perform the route recursion, otherwise the route cannot be used. So you have to know, like, okay, if I go through the recursion process, show BGP, I look at the routing output, it tells me this is the subnet, the next hop is XYZ. I do a show IP route for the next hop, it tells me it's going on gig 1 and that particular next hop is reachable via OSPF. or EIGRP or whatever the protocol is. So results in a failed next hop recursion if failed best path selection. So what's actually interesting about that if the next hop is not recursible, you'll actually get it as a, what's the command? It's not unavailable. What is that? I can't remember the output, what it looks like, but it's it literally. Let's see if I can't figure this out real quick. BGP next hop unreachable. That's what it is. It'll be an unreachable. So it'll show up. If you do an output, it'll tell you it's unreachable, which means BGP. There's no way to recurse to that IP. So when you have situations like that, there's a couple different ways to fix it. So the first way, so different peerings have different next hop processing rules. For IBGP, by default, outbound IBGP updates do not modify the next hop attributes regardless of the IBGP peer type. So what that means is if I'm an IBGP peer and I peer with a particular next hop IP, what will end up happening is if my neighbor, my peer, learns an eBGP route, that route comes in, they learn it, they send it to me, my next hop to that particular peer is going to be the IP address of the IP address that's associated to the remote AS. So neighbor 10.1.1.1, if that's the other router, that's going to be my next hop. So what's going to end up happening is every router in the autonomous system that's doing IBGP would need to know how to get to 10.1.1.1. If it doesn't, then you're going to have to do some modification. There's two different ways that you can do that. You can do neighbor next hop self. Say, hey, I'm the neighbor. Go ahead and tell your neighbor that I'm next hop is self. Or you can do another variation of that would be to go and advertise the external segment into IGP. We'll take a look at both of them, but that's essentially the issues that you run into. So if BGP doesn't know how to reach the next hop, it'll say unreachable. So then you have to circle back and go, okay, why is it unreachable? Oh, that's because that IP address isn't advertised into IGP or whatever the case might be, and then you have to advertise it somehow, whether it's next hop self or doing a route map action set IP next hop, so on and so forth. So there's a couple different ways that you can solve it, and we're going to be taking a look at that. So IBGP is more finicky about that than eBGP is, which is why a lot of customers opt to go the eBGP way because it's easier to work with. IBGP, again, has very specific rules where if you're not careful with it, you can handicap yourself. And we're going to take a look at a scenario, actually a few different scenarios, when we get into that particular part so we can understand how that comes into play. Now, I'm not planning on doing any hardcore service provider specific videos, which is what unified MPLS is. It's basically aggregated or scalable seamless MPLS. It's breaking up the MPLS VPN into different blocks, aggregation, core, distribution, stuff like that. So eBGP, on the other hand, isn't so finicky. And as a matter of fact, outbound eBGP updates have a local update source for the neighbor set as next hop. So whatever the IP address is in your neighbor statement, that is going to be your next hop. So you are always going to be doing that. You can modify this through a couple different ways if you want to do so, but in most cases you're not going to be doing that. So we're going to be taking a look at both examples and how they come into play. Again, so a project that I was working on not too long ago, where we ended up doing a whole BGP hierarchy in order to get a very large migration from IGP to BGP deployed, we leveraged eBGP everywhere because it made the next hop processing process of the next hop self for making sure that the local subnet is advertised, all that type of stuff. That goes away. That complexity goes away with eBGP. There's a question. You mentioned unreachable. I'm not quite attaching that. Okay, so what would be unreachable is the subnet itself wouldn't know how to recurse to where it's got to go. So essentially the idea is this. If I receive a route, if I'm over here and I get this prefix gets advertised into BGP from this guy to here. Right? Let me grab my pen instead of trying to draw with my mouse. Right? So this guy goes to here. Right? 29 gets it. He sends to 28. 28 sends it to 43. 28 sends to 61. 28 sends to 60. 43 sends to 27. And the control plane wise, the route propagation is going to happen regardless. Control plane propagation versus data plane reachability are two completely different things. And this is where it's a data plane reachability thing. So if I am doing the configuration here, or let's say, for example, I'm doing a full mesh appearing, like we mentioned over here, right? We get this all squared away. And then this subnet here is getting advertised into BGP this way. So I'm advertising this, and we'll say this is 102, this is 101, right? What's going to end up happening is I will get all the way over to here. And it could happen in this one too. But if I don't have a clearly defined next hop, when I receive the update, I'm going to receive 1.26.35.0/24. The route's going to propagate. It'll propagate, but when, say, R60 gets it, if he doesn't know how to get to this next hop, he's going to fail to, it's a failure to launch. He's not going to be able to recurse, so 60 needs to know the next hop IP address. So how do you get to 26? If he doesn't know how to get to 26, that's where the problem comes into play. So you need to figure out some way to do that. Either A, you take and you advertise the loopback address into IGP, or you need to come over here onto this subnet and advertise it into IGP so IGP knows how to get there. Once, the funny thing about this is, if you decide to go this route and advertise it into IGP, even though you're not going to be trying to form a peering on it, let's say you throw the passive interface command on this interface, but still advertise the subnet into IGP, that's all you need is reachability. It just needs to be in the routing table. You don't actually want to route traffic to the segment. You just want it to be reachable in the routing table. So you would advertise that into IGP, but then 60 would receive that and go, oh, okay, well, it's, 26 would then propagate that to 26 and 27. 42 would advertise that to 60. 27 would advertise that to 60. 60 would have then a route to this prefix by way of 42 and 27 to 26. Therefore, you would have reachability. So that's essentially where that would come into play. We're going to see some scenarios where that comes into play, and it can be tricky to troubleshoot it if you're not exactly sure what you're looking at and how it comes into play. So these are just some of the things to keep in the back of your mind when you are going through the details of how BGP works. Again, iBGP specific recursion issues. So eBGP doesn't have this problem. So if I was to say eBGP everywhere, we wouldn't have a problem. I could literally give every one of these routers its own autonomous system number and do full eBGP everywhere, and we would never see that problem. It would automatically just work. That's why eBGP, when you're trying to migrate, is usually the better choice when you're trying to do a BGP hierarchy than it is to go out and do iBGP to try to make things easier. Hopefully that answers your question. Let's go back over here. So by default, eBGP updates have local update source for neighbor set as next hop. If update source is loopback 0, next hop is loopback 0. This can be modified, as we said. BGP authentication is implemented through TCP option 19, the MD5 hash. Configuration is very straightforward. It only requires the additional neighbor statement with the password option. If the peering occurs, authentication is successful, and we'll take a look at that as well. So it would just be would be neighbor 10.1.1.1 password Cisco 123, something like that. So then we have the full mesh and the. Actually, I'm at a half hour now, so I'm going to stop it there. So I will talk about, yeah, I'll talk about full mesh and route reflection, scaling techniques, route reflector clearing, all that type of stuff. I'm going to talk about the next video because it's going to take a minute to go through that as well. And I'd rather not go through it. I'd have an hour-long video. I'm trying to make these a little bit more palatable. So if you guys have any questions on anything that I've covered so far, please leave a comment in the comment section below. If you haven't already done so, please like, share, and subscribe. And I'll catch all of you fine people in the next video.